Introducing Fred BB, an infrared detecting self-balancing robot. Our system revolves around two main components, balance control and search control. The balance control utilizes the accelerometer and the gyroscope. We obtain the values from the accelerometer and gyroscope, and we combine them using a complementary filter, which reduces the noise and the drift. Using these values, we derive a tilt angle A, and we combine this with the previous 8 recorded tilt angles in order to achieve an averaged angle F. This filtered tilt angle reduces the noise in our readings. We then use this filtered tilt angle F to generate a pulse for the servos, and this pulse is just F times the max difference divided by the range, where the max difference is the maximum amount of difference in the 0 position and the servo position, and the range is the full range of servo positions. Then we move the servos in response to this pulse, adding the pulse to the servo base value, which is the value at which the servos are stopped. The search control can trigger at any point in this sequence, and this happens when an interrupt is triggered by the IR receivers. An interrupt is triggered whenever there's a falling edge detected on one of the receivers. This basically means that the receiver goes from reading a 1 to reading a 0, which happens when it is detecting an IR light. Now, the interrupt figures out whether the signal came from a left receiver or a right receiver, and it moves the servos in response. So if it saw the signal from a left receiver, it rotates the servos to turn further left for 500 milliseconds, and if it sees it on the right receiver, then it rotates the servos to turn them right for 500 milliseconds. This turning is done using differential drive, where the servos are given various speeds in order to turn left or right in response to the IR values. Our design involves a couple of different components. First of all, we have the main base, which is the robot frame that we designed and 3D printed ourselves. Next, we have 2 IR receivers that are on the PCB. We also have an MPU 6050, which is our accelerometer and gyroscope that is also on the PCB. And finally, we have 2 Phytech FS90R, which are the 2 servo wheels that we can control. We also have a battery pack and the FRDM attached to the back of our robot. And we have a cute face on our robot to top it all off. This diagram goes into a little bit more description of how the actual electronics on board work. We have the 2 servos, which are connected to power, ground, and a signal pin. And the IR receivers are similarly connected to a power, ground, and signal pin. The accelerometer or gyroscope, the MPU 6050, is connected to power, ground, SCL, SDA, and an address pin in order to use I2C communication. And the battery pack is connected to power and ground. On the pinout of the board, you can see how all of the different pins are connected, including the PWN pins for the servos, the GPIO pins for the IR, and the I2C pins for the accelerometer gyroscope. Finally, we have included snippets of our code in order to show how we control the different parts of our robot. First, we have the interrupt code for the interrupt handler that we use in order to trigger the servos to move left or right in response to the IR input. We also have the code for the accelerometer gyroscope, which is how the I2C ports are set up and how we generate pulses using the tilt angle, as well as how we calculate the tilt angle itself. Finally, we have the code here for how we trigger servos to move, using the servo pulses and the servo move method. We hope you enjoyed looking at our project. Thank you so much for watching.